Thank you, everyone. Thank you for being here in this next Friday talk. Today, as a speaker, we have Giuseppe Sorrentino, second year PhD student at Politecnico di Milano here at DEI. And he's going to present us today his work related to federated learning applied to heterogeneous architectures. So thank you, Giuseppe, for being here, and it's your turn.
Thank you, Laura, and thank you all people online. I'm Giuseppe, I'm a second year PhD student, and today we will describe you the core of my research so far in Milano. Okay, presentation is working. So, the core of my research is about federated learning, not just federated learning as is, but accelerated through heterogeneous architectures. But before giving you more details about this, let me just introduce myself. I'm a second year PhD student at NextLab here in Milan. I was formerly intern in AMD and currently in Huawei to study and deepen different kinds of architectures. Indeed, in all these experiences, I could deepen my research topics about hardware-aware optimizations, so not only optimizing a kernel, but deeply apply the optimizations for the specific hardware substrate I'm using. Generally, I target heterogeneous systems, and in few slides we will have a clear idea of what are heterogeneous systems in this context. And the idea is to have distributed nodes communicating with each other. For all these scenarios, my target applications are about image processing and computer vision applied to healthcare systems. Just for giving you a bit of context, today in healthcare, but also in robotics, automotive, or in different scenarios, deep learning is the main kind of application that uses data in order to give us accurate results. But actually, deep learning was not born today. Deep learning was about 80s. Today, it's so famous because we have the correct hardware substrate, but also enough data to have it, train the models and then accurate results. But what if we do not have so many data? Actually, if you consider the healthcare system, for example, it is reasonable that in bigger hospitals there are much more patients than in smaller ones. And one possibility could be just moving data. But actually, we don't want to move sensitive information. And in 2019, also the latest GDPR has given a lot of regulations about how to move data, which is crucial. We want to keep our privacy safe. We want to keep our personal information private. To answer this problem, the literature proposes federated learning in general for healthcare in my research, but also in other kind of applications. Federated learning allows to share information about models instead of sharing the information about people, instead of sharing raw data. This has obviously huge benefits, but also comes with interesting problems. First thing first, these are a huge overhead. We need to secure information, we need to secure data. These privacy-preserving mechanisms have an overhead that can't be ignored. And also, even if you have multiple models and you want to combine them, it's not obvious that the final result will be better than the initial one. So also the strategy for combining this model must be deepened. In particular, in my context, I focus on an application about 3D image registration, which essentially consists on aligning a 3D floating volume with respect to a reference in order to correct misalignment, which are generally caused during the acquisition phase. This task actually has three main challenges about the accuracy of the overall registration, about the latency, as we have to consider the task as a crucial task for example, robotic surgery. So latency constraints are demanding. And also we want to achieve the lowest power consumption. Thus, my research here in Milan focuses on devising a federated learning system to generally improve the model accuracy for 3D image registration, trying also to mitigate the communication overhead that are introduced by the privacy-preserving mechanisms of such systems. Given this context, we have to establish which kind of federated learning we want to focus on. There are different kinds of federated learning. There is the horizontal federated learning, in which we have different samples, different people, if you think about hospitals, but same kind of features. In vertical federated learning, instead, we have the same sample of people, but different kind of features analyzed. In a practical scenario, if a subset of people has different analysis center, this may be the case for vertical federated learning. And transfer learning is a trade-off between the two. It starts with a horizontal step and then continues vertically. And given the three possibilities, the most interesting one for the federated case in horizontal scenario, in the healthcare scenario, is the horizontal federated learning. As actually the idea is, we would like to give also to small hospitals the same possibility of bigger ones, without sharing data from bigger hospitals. But in this kind of federated learning, we must be aware that sharing information may be consuming, may be demanding. There are different ways to secure the information. We may have noise addition that actually does not have an important overhead, but is not really the most secure way, or someone even considered blockchains for this task. Obviously, blockchains are probably the most secure, but on the drawback side, you have an overhead that it's very hard to mitigate. The best trade-off between the two, and also one of the most interesting technology for this, seems to be homomorphic encryption. Homomorphic encryption actually allows to work on privacy-secure data without sharing raw information. There are different kinds of homomorphic encryption. We have the partial homomorphic encryption, in which just a single kind of operations is allowed. We have the somewhat homomorphic encryption, in which you are allowed to do both multiplications and additions, that are usually the two most important operations in this context, but only a fixed number of times, as at each operation you apply, you are also adding some noise. This means that after a certain number of steps, you will actually destroy the information. And finally, literature came with the best homomorphic encryption model, the following homomorphic encryption, that actually adds to the somewhat a bootstrap step that permits to reduce the noise. This is the kind of homomorphic encryption I want to focus on along my PhD. The idea is to start by partial encryption and then reach the finally fully homomorphic one. There are different kinds of solutions. We have software-based solutions, hardware-based solutions, and on the other side, we mainly have FPGA-based solutions, which have remarkable flexibility, or ASIC-based solutions that usually targets very high performance and low power consumption. Given the context, in my federated learning system, the first analysis of my research started by the architectures. I had to find the best architecture for this task. Considering 3D image registration, the task I'm targeting, we have two main steps. A rich registration step that is like processing, and it actually is applied through a heuristic step, so a set of optimizations, and a deformable step, which is usually performed through deep learning. Well, what we know from literature is that for deep learning, usually GPUs are the de facto standard. So we want to use GPUs for this task. But if you look at rigid image step, this is much more complex, because actually FPGAs prove to be effective for this task too. However, as also said in the beginning, we want to target heterogeneous systems. So why not having both of the architectures? And this is actually a choice. We may have multiple architectures. The problem in this scenario is that to make the two architectures communicate, today we need to use CPU in the middle, which strongly degrades performance. So my technology choice for this research is about versatile systems that actually merges the benefits of FPGAs and GPUs without really suffering the drawback of having a CPU, because actually everything is combined in a single heterogeneous device. However, targeting this kind of architectures, this kind of heterogeneous systems is challenging. There are challenges about how to partition an application across different hardware layers. Indeed, in a versatile system, we have the FPGAs for flexibility and AI engines. AI engines can be seen as a lot of small cores that allows you to give a lot of computational capabilities thanks to the vector units and parallel APIs, but they must be properly exploited to avoid any kind of deadlock and problems when making these two architectures communicate. Indeed, they are very different. FPGAs on the side, on the right side, generally allows to have a very flexible design, generally works around 250-300 megahertz, while the AI engines are stuck on 1 gigahertz of working frequency. So even just this simple difference makes the communication harder. Then, if you consider a real application, you have to understand which part of your design must be tailored per each layer, trying to mitigate as much as possible the discrepancies. Given this complexity, one of my first work here in Milan was finding and devising a toolkit for both education and design in order to simplify the usage of virtual systems. This research, currently accepted at ISCAS and will be presented in a couple of months, actually allows to algorithmically split the design step for virtual systems in well-defined part. We have the AI engine step and the FPGA step, which are almost independent, even if our toolkit suggested some guidelines for mixing the text, avoiding and at least anticipating as much as possible some issues to allow the programmer to solve it. Then we have a linking step in which we can merge together the results of the previous two phases and the deploy phase in which we are actually able to emulate or execute on the real hardware our design. Just from this picture, it's clear that we need to care about a lot of different parameters, which may be related to the AI engines or the FPGA. Therefore, we also devised a design-space exploration strategy that allows to algorithmically define optimal designs by scaling parameters from both FPGAs and GPUs. Generally, this design-space exploration strategy starts by analyzing how the FPGA accesses memory, which usually is a bottleneck for most of the applications, and once these performances are satisfied, it starts increasing the number of AI engine kernels employed. The idea of AI engines is to split the workload across multiple compute units. This means that the number, of course, strongly affects your overall performance. We also apply this methodology, both the toolkit and the design exploration, to real cases, in particular, also for some courses here in Milan. We have devised a library for similarity metric acceleration on AI engine, targeting different libraries and proposing a MapReduce approach, which properly fits the architecture of virtual systems. As you can have FPGAs for properly distribute your data across multiple AI engines, and then the AI that actually can execute the workload. This is about the architecture, but obviously, focusing on a single architecture will strongly limit the research itself. Because actually, the virtual systems tomorrow may be different or may be removed. If we analyze the system itself, the main reason for using a virtual systems was to avoid the CPU in the middle between FPGA and GPU in a heterogeneous setting. Thus, during my internship in AMD, I also focused on a peer-to-peer product about making these two devices communicate without involving the CPU. This means that what you are now doing on a single device between FPGA and AI engines may be also transposed on heterogeneous systems in which we are merging FPGAs and GPU capabilities. Once solved the target and the hardware challenges, then I have to focus also on the application side. For giving you multiple details about this, you can consider about the 3D image registration as a huge application in which you have two sensors that acquires the two volumes of images. These images are given as input to the preprocessing step that actually is performed through an heuristic. So you apply several transformations to the protein volume to align it with respect to the reference volume according to a similarity metric. And as metric, I target the modal information as it gives me the multimodality feature. So the two input images can also be acquired from different sensors. This preprocessing must be repeated, this preprocessing requires to repeat multiple times the transformation and modal information step, but the final output will be a floating volume in which the rigid transformations, the rigid deformations are corrected. And the output of this can be given as input to a neural network for finally complete the registration step, correcting also non-rigid deformations. Deepening analysis, we have that even if the algorithm seems to be quite balanced, actually it is not. Because the preprocessing step takes almost the 80% of the entire execution time, and most of the existing non-rigid extension work gives it as granted. But in our case, as we need to integrate the overall application into a more complex system, we cannot just ignore preprocessing. So we need to accelerate both tasks. And while for the fraud registration, we already know that GPUs will be de facto standard, the analysis on the rigid registration step is much more complex. Indeed, I analyzed several state-of-the-art solutions, discovering that for the transformation step, GPUs are still de facto standard, proving that actually they are very valuable for my research. But looking at modal information, the game changes, because actually FPGAs outperform GPUs. As a result, we have an architectural dichotomy, and also we would like to use FPGAs, because FPGAs today are the de facto standard also for the encryption tasks. Thus, I partitioned the application across different layers of virtual systems, leaving the modal information step on FPGAs as it is in the state-of-the-art, but using the AI engines for the transformation step. This first research has been presented a few months ago in SCD here in Milan, actually consists on computing transformation on the AI engine, producing the coordinates which are given to a programmable logic component that fetches memory properly applying transformation. This is fine, but the main problem with transformation alone is that it degrades the image quality, thus we need interpolation, which makes the game a bit more tricky. Because if you consider the transformation, and this is exactly the kernel of transformation I presented a few slides ago, we need to apply some sort of interpolation strategy. And I decided to apply linear interpolation, as actually it's represents the best trade-off between computation overhead and accuracy. But it requires 4 transformed pixels combined together in order to compute a single output value. In practice, on the design, this means that we need to have 4 times the transformation component, accessing 4 times the memory, and to mitigate this access, we are actually using different memory ports, trying to reduce as much as possible memory pressure, and we are adding some pipes between PI engines and PI kernels in order to avoid the loss. Also, as we need to compute the factors for the interpolation, we must be care about the algorithmic structure. General interpolation can be seen as a consecutive step of transformation. But actually, we want to overlap these 2 phases as much as possible to reduce the overhead of interpolation. And looking at formulas, the weights can be computed in parallel as they are completely independent from the pixel values itself. So while the PI components are computing the transformation, on the AI engine part, we can compute the weights for the interpolation and properly reordering data in order to simplify the communication between the kernels. Then, for the last step, weights and pixels must be combined together for the interpolation step that gives the output the interpolated volume. This last component is named interpolation processing element, and actually it is designed to be scalable, because here we have the bottleneck of the whole application. We have floating point computations, we have multiplications, a lot of pixels combined together. This means that we need to be able to scale this. And actually we can scale it up to 52 interpolation processing elements working in parallel and giving the output of this interpolation to the literature model information kernel that actually performs 3D model information computation. The two steps, the two accelerated steps, represents the registration step entirely accelerated on the single universal system, and once integrated within the software application, it actually allows to accelerate to perform the whole 3D rigid image registration. Looking at the preliminary results, for the transformation step, we are almost 40 times faster than existing GPUs and FPGAs and even software solutions. And these performances are actually the same also considering the registration step, as the transformation itself is a bottleneck. The game changes a bit more when you consider the whole application, as now, differently from what happens previously in literature, the software component is not negligible anymore. We accelerated so much the register that now the workload is, the overhead is almost the same on the software and the hardware part. But still, in this case, we obtain an average 2 times speed up with respect to existing literature solution. In terms of accuracy, we can mostly focus on the transformation part, as the model information has already improved in literature. And our transformation has a lower mean square error with respect to existing solution than the mean square error between them. This means that for this kind of tasks, as we can use MATLAB Cornea, we can also use our transformation safely. And these numbers are also proved considering the registration accuracy, as we attain an average of 98.8% in terms of intersection over union. This is about the rigid step, but also considering the federated learning system, along my research so far, I also had to focus on the communication part, on the encryption part. We started focusing on CKKS algorithm, as it guarantees post-quantum security, post-quantum cryptography for our data. We are targeting both embedded systems and HPC systems, in this case, universals. The idea is that homomorphic encryption is surely crucial for my research, but it is generally applicable to different applications. Thus, I would like to have embedded systems on the edge that can actually perform encoding and decoding, and more HPC systems on the cloud that can combine data through operations. Today, we have just the partial homomorphic encryption. Actually, it's still a work in progress research, but the idea is that once we will finish the partial homomorphic encryption, we will also extend it through somewhat and finally up to reach the full homomorphic encryption. This was mainly my research work here in Milan so far, actually last year, because now I still need to focus on the application side. Because I presented you just the rigid part, but the rigid part is yet just the first of the 2 steps of the whole application. This means that somehow I need to apply the formal registration on FPGAs. First thing first, I need to understand which kind of network must be used for this task. And actually, UNet seems to be the best choice for 3D image, generally for 3D image-based networks, but in particular for 3D image registration, as there are a lot of open source solutions as Voxemon that already provide non-rigid support for non-rigid 3D image registration. However, again, the hardware for this set are GPUs, so we need to find a way to map this network, this deep learning network, on the FPGA. We don't need to invent the wheel from scratch. Actually, we can use mapping tools for FPGA. There are tons of them. We may have FPGA CompNet or HLS4ML, or also FIN, and other them, which may target different kind of features and different kind of networks. Thus, my research now is deepening these kind of tools to understand which one properly fits my tasks. And actually, I was already able to discard some of them, as, for example, HLS4ML has much more support for 2D cases than for the 3D ones, while FIN mainly focuses on binary internal networks and still does not seem to have support for 3D networks. Thus, the idea today for my research is to map the UNet network on the FPGA through or FPGA component or Genesis. But again, if someone has ideas or knows about tools for this task, just feel free to drop me an email. This is still ongoing research, so more than happy to collaborate or evaluate other options. On this case, the main question now is how to do this? Because actually, we need some sort of intermediate representation for this task, and I'm focusing on ONNX intermediate representation in order to transform a network in a proper graph that can be used by the tools for mapping it onto FPGAs. Thanks to this, I will be actually able to combine effectively the HLS output from these tools within the rigid pipeline and complete the federated learning step. The whole will be also integrated with the CKKS homomorphic encryption tasks in order to actually create at least small networks in which multiple devices are targeting these kind of applications, in particular the image registration, on a single or at least heterogeneous systems. In the meantime, I thank you for your attention, and if you have any kind of question, feel free to ask, more than happy to answer.
Thank you, Giuseppe, for your talk. I don't know if there's any question from online. In this case, you can both use the mic or use the chat. In the meantime, I was just wondering whether you have thought or you know what can be the role of the FPGA in this whole context.
Yes, thank you for the question. Actually, during this year, I have a slide for this, because actually during this year, we also have different kinds of applications between FPGAs and GPUs. And the best discovery in this case was that the main computation can be tailored on AI engines as they have a higher working frequency, but AI engines are not so flexible. They must know about a lot of different parameters because they need to perform some static scheduling. Thus, the FPGA is the best hardware for reshaping data, moving them in the correct shape, moving them in the correct way, and distribute them across multiple AI engines. Here, for example, I'm presenting just the K-means clustering case, in which the AI engines must be aware of points and clusters, actually, but they must be handled differently, so the AI engine must know a lot of information about what are real points, what are not real points, because you need to apply some clustering in order to exploit the vector unit of AI engines. So, in just few words, the idea of FPGA for me is that it will be the turning point for really properly use the AI engines by handling data through its flexibility.
Thank you for your answer. So if there's no other question from home, I think that we can finish here. So thank you all for being here, and of course, thank you, Giuseppe, for this. So thank you, and see you in the next Friday talk. Thank you.